Hello, I hope y'all are doing well. So I wanted to create this video to walk you through pretty much the entire ball on the floor experiment. Some of you collected data in person, some of you collected the data from the Desmos. Either of those is fine. You still got good data. I'm going to show you what I expect your graph to look like. And if it doesn't look like that, then I would like you to collect the data through Desmos instead of using your in-person data. So we come here, we go to modules, and I'm going to show you the slide for 920, but really this is going to be for the gold day of 920 and then also for the blue and gold day of 921 and 22. So the same video is going to be on all three pages to help walk you through this activity. So if you click on this, it has a ton of words, which is why I'm talking to you like this. So hopefully you brought headphones here. Not everyone is listening to me right now. All right. Yeah, we're going to learn how to model the distance a ball travels as it rolls across the floor over time, justify your level of confidence in your prediction, and make a data-informed prediction, communicate level of confidence, and effectively justify your level of confidence. So we start with the do now. You can take a minute, pause the video, write this answer down or write these answers down in your journal, in your notebook. So pause me. Cool beans, let's move on. Hopefully you got some good stuff. I was gonna say it, but I don't want to just in case you were waiting for me to say the answer. So I'll let y'all do it. Hopefully you can figure out which one you're more confident in based on the confidence rubric we've done before. All right, so for my students who are my blue day students, my odd 1, 3, 5, 7 kids, you should have had a chance to look over some of the slides and start in with your Desmos. I've put the enrollment codes just in case you need them for Desmos. But in these slides, yeah, right here, 2 through 6, start with what we talked about. We did this as our warm up. We talked about this. We had some good questions that y'all came up with, so we added those in here as well. And we came up with how far is that object going to travel in 6 seconds. And we're going to guess that based on the information you get from your graph. So we had what our independent variable is going to be is our time, and the dependent variable is going to be how far that object rolls or how far that bowling ball rolls. So what do we intelligently think is going to happen? So I think as time increases, the distance is going to what? Increase? Do you think the distance is going to decrease, or is the distance going to stay the same as that object continues to travel? So you can take a minute, pause the video, think about that. All right, moving on. This is where we do the data collection. So if you were in person with me and you decided, man, I really want to conduct an experiment, and you did, and you got some data, then you can enter that into the Desmos in the same, I'll show you now. You can enter that into the Desmos on slide 5. So make sure, and this is so very, very important, if you are starting your timer at the top of the ramp, that is not going to work. You need to start the timer when, so if you were in person, hold on, you would need to start the timer when that ball is first on the horizontal surface. So if you started it at the top of your ramp, you need to subtract the time it roll down the ramp from each of your time segments. If what I said did not make sense, then I highly encourage you to choose either A or B based on your last name and collect the data from here, because it's going to start at 0 seconds once that bowling ball is off the ramp. So you're going to collect your data. I'm going to throw out some stuff here. Hopefully this doesn't look too bad. I'm making it up as I go. And let's go 1, 5. And 5. 2, 2.5. All right, so let's see what happened. I'm nervous. Do not use those as your data points. Those are straight from my brain. That is not part of your experiment. That worked okay. We'll let it work. That was not good data. I'm going to steal one of yours because some of y'all have some good stuff. Teacher. Yes. This one, whoever this fake person is, has beautiful data. This is what we would expect. I'm going to go to their slide 5 and see their data. Don't steal it. All right. So they got some pretty good data. They've got some pretty good results. And this is what we are looking for is when you're sliding this A slider bar after you've collected data, and we're looking for that A slider bar to go through the majority of most of those points. So one of those best fit lines, I would say this red one is pretty spot on. Blue one, we can make it go away. And that's the only one we've got there. So now, once each of you has your own data, we're going to have people that have the A video, people that did the B video based on your last name. We're also going to have groups of people who conducted the experiment in person. So we're going to have some of you that have 10 centimeters high as a release height, and some of you have 20 centimeters high as release height. So this is what I am saying. We've gone through all of this just now, and we are right here at slide 6. So we're going to start in with this lower portion. Again, pause me when you need to. Make me go as slow as you need so that you can make sure you're staying on top of this. If you need to pause me at any point, I'm not offended. I'm not even there. Sorry, I make myself laugh sometimes. All right, so we're going to continue in with the agenda for today. The big part that y'all are going to be doing is this data discussion slides. So this is something new. This is helping you understand what the mathematical model means. And to do that, we're going to be comparing some points. We couldn't really do that with the pendulum experiment because we all had the same angle and we all had the same data. But in this case, we're going to have in-person groups. You can see here with 10 and 20 centimeters. We're going to have Desmos groups of 10 and 20 centimeters. And y'all are going to pair up together and compare your results so that we can start identifying what do these patterns actually mean? What do these data points mean? What are they telling us? So, and then we're going to get an idea of what our new graph shape is and why it's important. So if you need to pause me, go for it. Otherwise, right now, you should have data from this slide or from the in-person, making sure that if you have data that you did in person, that your line is going through 0, 0. The reason that is so important is because at 0 position, we should have had 0 seconds. Again, if it doesn't, then you are going to do one of those 2 videos on the previous slide and collect that data and use that. So this is what we are looking for, is a nice graph shape. Then you are going to come in and open up the data discussion slides. So take a second, open those up. There's a lot of information here, which is okay. Y'all are going to pick up a data discussion ball on the floor worksheet from the sub, so go gather that. Again, your grouping requirements, I'd like you 4 people or less. Y'all don't need to be in a big group of 8 or 10. So remain socially distanced to the best of your ability. Try to collect your data and do your data discussion in less than 15 minutes if you can. That's why I want those groups small, y'all. All right. So my 2 main requirements are right here. Oh, I guess 3. So go get that paper, open those slides. If you are with a group that is not your table, please write down who you are working with. Y'all know what that's about. Good old contact tracing. So data discussion slides opened and let's roll. Well, oh, sorry, I thought it was in the big slides. No, little slides. So data discussion. We're going to use these slides as our data discussion guide. for this data discussion template that y'all should have grabbed from the sub. So you have this in front of you, and we are going to go through first determining data points from each group. You can use those data points to help you compare the information. You're going to summarize how your mathematical model compares to the class average or to your peers that you're working with. You don't have to run around and get a number from every group member, just from the people that you're working with. A diagram of the setup, literally chair, ramp, ball, floor. Your data points. Plot your graph here, please. I'd like to know the mathematical model for group A. So I believe, if I had to guess, those were our, going back to checks, I don't trust myself. A was the low ramp. All right, so 10 centimeters. And B was our 20 centimeter. So in here, I'm going to say mathematical model for A and mathematical model for B. Where might you find that mathematical model, you may be asking? Back to your Desmos. Go back to slide 6. And your mathematical model matches the line of best fit. In this case, the line of best fit is my red line. So I'm looking at my red equation there. And I have that D equals A times T. So if I look on my, I never know what to call these axes, the label on my y-axis is going to be distance. Label on my x-axis is time. So hopefully you're looking at this D equals A times T and you're like, cool. D probably means distance, T probably means time, and A is that constant value that you got above. And if you did think that, I would give you like a massive high five because you're right. So let's write that down below. Right here. Just B equals, but we're not going to write A because that's the equation. We know A. So it's 1.6. Oh, man. You don't have to do the parentheses. I'm just a weirdo about that. Sorry. So our distance is going to be equal to 1.6 times the time that it's rolling. All right. So with this information, you can write this on your data discussion for A and B. Because you had different heights, you should have different A values. That's what y'all are going to figure out what they mean. So the data discussion slides then kind of start in with, hey, we're walking the triangle, understanding what's going on. So we've got the experience or the phenomenon. We watched it. It was a ball going down a ramp. Graph, we just created that. That's your slide. I'm not lying to you. I think it was slide 6. And then the mathematical representation, that's what we are working on now. All 3 of these are going to point to like an understanding, a deeper understanding of what your graph is telling you. So slide 3. This is looking at, if we were to superimpose an A group and a B group on the same slide, we would have something like this, to where one of them is going to have a greater slope. So hopefully you're already like tying in what you think that slope represents. It really does tie into some of those questions y'all asked before. So we're going to do some quality control of the data in the graph, comparing your A. Yeah, we can do that. Your A to another A. Again, make sure that you are both online or both, like from the Desmos video, or both in person. In person wouldn't really work though. So if you did online, you can compare A and B and B. And then we're going to orient the data. So making sure the scales are the same so that you can compare the data. Doesn't really work if you've got 0.5, 1, 1.5, and 2, and the other person has 2, 4, 6, 8. It's going to look a bit different. Okay. This is what y'all are working on now, finding those similarities and differences. What is the same and different between group A and B? So back in your sheet, that's what y'all are looking at here. What is the same? You could say, I don't know, I'll give you one. They both have the same shape. What is the difference? They have different slopes. So you can bring in some data points to help support your answers. but you're going to continue with the similarities and the differences here. For each of the bowling ball, predict the distance the ball will travel after 0.5 seconds. State your confidence for that prediction. Oh, it says for each ball bearing, that should be bowling ball as well. Or whatever ball you used in your in-person one. Predict the distance the ball will travel after 10 seconds and state your confidence. So again, for this, you're going back to your graph and you're looking at, well, where does 0.5 sit within my data? And zoom out some. How confident are you at 10 seconds? Way out here. So 0.5 and 10. Hopefully you can look at that and give a pretty accurate, whatever that's called, pretty accurate guess. All right. So we're going to continue on with this. It says complete the Desmos card sort. You can go do that now. That would work. Back in Desmos. Actually, I kind of want you to hold on till the end. Don't do that yet. Maybe I'll erase that part. So in words, describe the A constant value for the following three contexts. So this is where those questions for the mathematical model come in. So in that mathematical model, it is, what is the A value? So from here, same questions, these four. What does your A value represent? We've got the distance it traveled and how long it took to get there. So in your idea, in your group, what does that A value represent? I'll pause it. I'm not going to give you all the answer. I'm giving you time to think about it and come up with what you think it should be. If you have questions and you want to text me to make sure that you are right, I will answer that and say yes or think again. But y'all should have me on my mind. So feel free to text and ask if your guess is correct, and I will tell you. So pause and think, talk to each other. All right, let us continue. In the graph, it shows up as what? So how do we see this A value represented in the graph? You may say, oh, this sounds like very familiar to what I had before, and it could. It could be something different. So again, if you want me to verify what you put down here, I'm happy to help you out. I want to know, how does your A value show up in the graph? Make sure you're pausing and talking to each other. That's why you have groups. Scientists do not work alone. Sometimes they do, but not here. So in the real world, it means, so what does that A value represent in the real world? We watched an object roll across the floor and we were reporting how far it could go in a period of time. So in the real world, what were we looking at? What were we trying to identify? What were we trying to figure out with this data that we collected? So pause the video, discuss with each other. All right, when you got that done, now you are going to take a moment to write out the equation using all words or concepts. So up here, you are going to write down that D equals whatever your A value was times T. So now down below, you're writing out what that means, pulling in the information from the previous boxes. When you have that done, you can move on to explain the pattern. Why does the pattern in the data make sense? And I know this is probably one of the hardest ones, and I understand that. I really, really do. But it's so important I don't want to say struggle with it, but it really is important to struggle with that one for a bit so that you have a deeper understanding of how to read your data. So again, pick a couple data points, compare them. What do you notice? Why should that make sense? Hopefully you're pausing, not just staring at me. Okay. So the next portion is all about your confidence and your justification. So if we come back, you should have the data discussion done. And you can, if you would like, to insert that information into your Desmos. Once you like fine tune it, kind of come up with a consensus, you can check with other people in class if they got a similar thing. Keep in mind their A value will be different, but you should all be on the same path of understanding what this A value represents and why it makes sense. So take a couple minutes, go check with your peers. If people aren't where you are, just check with somebody who seems like they might be at this point. Pause. And moving on. This is key. Please make sure that y'all are working together. I know that that room is probably dead silent right now, or that y'all are talking to each other about off-topic things, if you've even gotten this far in the video. But y'all are a group of scientists working together. I'm not going to be there for a week, so y'all really do need to be working with each other and not being stagnant, because we don't have time to catch up. We got to keep on moving. Again, reason for the video. All right, so the last little, let's see if I missed anything here. We talked about that. Oh, it gives you more information and more kind of guiding questions. So y'all can go there. Compare your A to another A, or B to another B. I said skip this one. Review your experiment. Oh, this is so beautiful. Make sure that you do these. Describe one data point for the same time variable, two distances, the same distance. What are the two time variables? Describe what trend you see in your data. I should have mentioned this before. This is so important. What is similar? What is different? Take a second to organize this little card sort. So the best way to do this is kind of up to you. You can go fastest, medium, mediumist, no, medium, and then slowest. And how would you determine which graph goes with that? I'm sure some of y'all are like screaming it in your head right now. I'm just trying not to say it out loud because I know what it is too, but I don't want to say it. Okay. So you're going to match up the graph with it, and then you can use the data points on the graph to help you figure out what your mathematical model is for that graph. So that way you're starting to understand, okay, fastest is going to be distance equals this times that, slowest is distance equals that times this. So take a second to do that. And then again, make sense of those datas. Good job. Data. So these are the same questions that we were just going over in the data discussion. All right. So I cannot stress enough how important your data discussion is to understanding your mathematical model. All right. So then we come back over here. These are the day 4 slides. Going past day 5. So we're around slide 21, 22, and slide 24 through, yeah, kind of into the 30s. Let's look. 33. 24 to 33, we're looking at how do we determine our confidence. This should look the same as what you have on your screen now in here. And we determine confidence. We talked a little bit about limitations in class. That rolling ball or that bowling ball in the video cannot act linear forever. It can't have that same pattern. Friction is going to start slowing it down. There's going to be some wind resistance that's slowing it down as it travels. So you may start to notice with your graph, and I did notice this with 1 or 2 of you that did this in person. Your graph had this beautiful shape, and then it just kind of started to curve off. So we were looking at a pattern almost like this with one of the data points, and that's okay. We expect that. Just don't try to match that pattern, because it's not, at this point, it starts to wear down. It doesn't make sense anymore. So we're focusing on the pattern that did make sense. All right. So what range does the model work well? Works well until about 17. After that point, it does start to break down. What else is important to consider? Considering that that system is non-sustainable. Hopefully y'all can look at this and say, oh, one of these has such beautiful data and the other one is a little off. And then that prediction. So the big question was, how far is that bowling ball going to roll in 6 seconds? I'm going to come over here now to Desmos. So in 6 seconds, I'm trying to back out a bit. Here we go. So you have your data range and you have your predicted value. When we are determining confidence, the only information we had last time was right here. We didn't have any of this stuff on the left. The only information we had, whoops, come back, was these 3 images and the fact that the value was within the data range, near it, or way outside of it. What we are bringing in for the rest of our units is this portion on the left, the second considerations, not just where it is in terms of the data points, but also where it is in terms of the best fit line. So we have a couple options. We've got our first one, which is the best fit line is near the center of nearly all of the data points, meaning we have some pretty good data. So it's going to be, I always reference Battleship, but some of y'all don't play Battleship, so I'll have to like show you with my hands. And then the second one is the best fit line is near the edges of many of the data points. It's close, but it's not through any. And then this last consideration in the like left column is that there may be new physics to consider. So the best fit line, it doesn't apply. Like they're all over the place, like a big old scatter plot. So we look at both. And if I was going to look at this graph, I'm not going to give you the answers, but if I was looking at this graph, it goes through pretty much all of those best fit line or those data points. So if I'm coming over here, I'm going to say, yeah, it looks like this top one. So then I'm in this row, and then I'm looking at where I am within the data range. Am I close? Am I within it? Am I near it? Or am I far from it? And that's where y'all are going to take your guess. All right. So use the pattern above to make that prediction, the prediction with justification with your confidence. So before we had discussed where you can say, I am blank high with my confidence. So medium, high, medium. So you can do the same thing here. I predict that the bowling ball will travel, let's see what we might think. Somewhere around 10 for this data set. It's different for you, whether you did in-person, online, A or B. So this person could say, I predict that at 6 seconds, the object will travel about 9.5 meters. And then you have to continue. I am, what's your justification? So yes, it is on this line. I'll give you that. It's one of these. So you'll say, my guess is I'm going to choose this one. This is not correct. Do not choose this one. I'm choosing this one as a very bad example. Don't choose this one. So I would say my prediction at 6 seconds is it'll travel 9.5 meters. I am extremely low. My confidence is extremely low in this prediction because now you're going to say both of those considerations. Because my predicted value is far from the data range and there may be new physics to consider, so the best fit line may no longer apply. So you're going to bring both of those statements in to make a little word sentence thing. All right. So what are some concerns or limitations you see? Actually, We can leave off these last two questions. You do not need to answer those two. I am taking this off. All right. So hopefully you feel confident with making your prediction. Hopefully now you have taken your data discussion from the paper. You thought about it for a few minutes and you've written that down as your mathematical model in Desmos. And if you have not done that, pause the video and do that now. Okay. So the next thing that we are going to do for this activity is a conclusion sort. Kind of how do you organize your claim, evidence, reasoning, mathematical model into one cohesive CER? So instead of saying, hey, go write it now, you get to move things along and card sort it. It's a Desmos. So if you wanted to go back to the home screen of Desmos, I will show you exactly where to find it. Sorry, I heard my son say shark and now baby shark popped in my head. It is not that I want to sing baby shark. So if you heard me humming, I apologize. Sad day in my life when I start singing that. All right. Oop. Nope, nope. Go to another class. Y'all aren't like, oh, I saw that. No. Let's see if I can pause share, turn that on and anonymize it. All right, so resume share. There we are. So we've got anonymized. Y'all don't know who these people are. And we're going to look at the ball on the floor card sort. It's going to be the same color as what we have over here. For our claim is red, evidence is yellow. I say this. Yes, okay. So claim is red, evidence is yellow, mathematical model. So your reasoning is green, your prediction is blue, and then your confidence with justification is purple. So they should line up into three separate columns. Really, if it's your highly confident one or high quality CER, you're going to see it kind of needs two columns to make that happen. So skeleton of a conclusion, kind of what should be in there. Oh, don't look there. So let's do that card sort. Go into your Desmos, find the one that says ball on floor conclusion card sort. Take a few minutes to organize your stuff. You can drag it and drop it where y'all need it. See, I just did it again. There we go. And then if you drag it and kind of it highlights that neck, like that top one blue, they will come in, like they'll stack together and it's really nice. And then you can move them as a whole instead of having to continually move one at a time. And if you think that you are incorrect, then you can move it out. So what I would do is start one at a time and look at my red ones. Oh, I can't even find my other red one. Is that it? Yep. So which of these looks like the highest quality claim? And then you'd be like, ooh, I know it. When you know it, you're going to pull it over and stick it with the high quality and then organize the other ones and do the same thing. But it really helps if you have them next to each other so you can see kind of what a high quality, low quality, and medium quality one would look like. So that's what I suggest to you. So again, take a couple minutes, make that happen. Pause and unpause. So then we're not having you write a CER for this. Remember, you are going to have a quiz over this. So I don't mind letting you see what a quality one would look like. You can scroll down and see, you can spend some time looking at it. And the good old question, if we're making this prediction at 6 seconds, is this still considered a wild guess or are we in the data informed prediction area? So we took some measurements, we utilized mathematics to find a pattern, and then we're predicting the future, predicting what should happen. So hopefully y'all are feeling a little bit more confident with this, at least more confident than you were the first one. Again, I cannot stress this enough. If you have questions while you are watching this and pausing this and working, send me a remind text. I'm happy to answer it. The only time I won't answer it is when I'm having surgery. Other than that, I will respond to you pretty quickly. So the last thing that you are going to be doing today is this slide. So you should have in your notes where we've already written down the constant horizontal pattern. This is our next pattern. This is the proportional pattern. So what I want you writing down from here, it's going to look very similar to what you had on the last one. So there was one slide up here that I wanted to pull one thing from right here. That we can call it proportional or linear. And, oh, I get it. Okay, so we can call it proportional or linear. And we are looking at a rate of change or slope. So you're going to draw the little hoop, draw the little graph, write that little statement. Pardon me. And then y'all are going to meet me on slide 39 and we're going to finish this up. So they call it either the linear or proportional. This one is proportional. You could put your own data that you got from your Desmos in here. I am perfectly fine with that. Or you can put what this data is, as long as you're understanding that there is a relationship between what's being put in and what you're getting out, if that made sense. You notice at 0 position, there is 0 time. At 1 meter, there, at 1 second, it was 5 meters. 2 seconds, it was 10 meters, 5 seconds, 25 meters. So writing down what your Y and your X are, I would put down what they were from your experiment, or you could put down independent and dependent variable. Write down your equation, put a box around it. So the whole point here is that you know that you're not just going to put Y, you're going to put whatever the name is here. In our lab for this, it was our distance. So we had distance equals A times X, which was our time. Oh, come back, little friend. So this bottom little graphic here is kind of nice. It's showing that, well, the distance is going to be 5 times time. We notice from these dots that they're pretty much the same distance apart. So what we can conclude is that when my X doubles, my Y is going to double. And we can confirm that by looking at X position 1 and position 2. At position 1, I was 5 meters away. At 1 second, I was 5 meters away. At 2 seconds, I was 10 meters away. So as my time doubled, my distance doubled. All right, so have that in your notes, ready to go. This video again should last you for, if you are my odd period, so 2nd and 8th, this should last you for Monday and Wednesday. If you are my even period, or sorry, why did I call y'all odd in 2-8? Wrong. If y'all are my 2nd 8 period group, this will last you for Monday and Wednesday. If you are, I think I did it again. Don't listen to my even odd. If you are my odd group of 1 and 7, then this video should help get you caught up from Friday if you felt lost. And it should also be enough for your work on Tuesday. If you still need more time with it, you can work with it on Thursday as well. But by Thursday, I expect that my 1st and 7th period are done. And by the end of Wednesday, I expect that by the end of Wednesday, I expect my 2 and 8 or 2nd and 8th period classes to be done with this. So we can then review and then move on to your quiz. This was a long video. If you stayed with me, I appreciate it. Only for your benefit. All right, y'all, take care.